let's talk about framing ILP as a satisfiability problem. So of course, we all know satisfiability is finding an assignment of Boolean variables that satisfies a given formula. And so this is kind of the approach they take. So first we have this idea of a template. A template is specifying a way to generate clauses, candidate rules. Okay, so we have, so for a given template, there is a whole bunch of potential rules based on that template that we want to consider. And so what we do is with each clause generated from one or more templates, we tack onto that clause one more ground atom, and that's a flag, okay? So we don't consider any constants or variables with this ground atom. We just treat it propositionally or as a predicate with, no arguments. So what we do is we're looking to find assignments to these Booleans such that the resulting clauses that have a positive Boolean associated with it union with the facts entail the positive examples. So essentially what we're saying is, we're saying that, hey, our solution to this ILP problem, it's this whole huge program consisting of all these clauses generated by the templates. And with each template, there's just an additional atom. And so the ones that have the positive, those are going to actually work. Everything else is essentially switched off. But the way you need to think about this to understand the learning is all that stuff from the templates is in the logic program. It's just that extra atom shuts some of those things off. The whole training process is trying to figure out which ones are turned on and which ones are turned off. So that's kind of the basic intuition here. And this was actually introduced in the 2015 paper, but it wasn't solved with the neural architecture. I think they used, like a integer programming sort of thing. All right, so let's make this concrete. Let's give an example. So we have a target that is Q, predicate Q. We have the extensional predicate P, and we have constants A, B, C, and D. All right, and so this is pretty much it. The slash is the number after the slash is the number of arguments for the predicate. All right, so let's say we have the following ground facts. PAB, PBC, PCD. Okay, so we're going to just work through this one example. And we have the following positive examples, and then the negative examples. All this is saying, and using this non-ground notation, is it's just everything that's not in the positive. Okay? So we're going to assume two templates, and here is template one. So for the templates, they put different requirements on the templates in the paper. This one of them is the number of existentially quantified variables in the body. This will have none. An existentially quantified variable is just saying, hey, let's say if Q of X is in my head of the rule, I can have an atom like P of XY, which will mean either, there exists a Y, well, in this case, if you extended it more, you could even say for all Y, but they look at the existential case. And no intentional predicates in the body, okay? So this template does not support rules that will be used after the first step of inference. It can't be because there's no intentional stuff in the body. So in the notation from the paper, this is what it looks like. They have tau, and they say V is 0, and int for intentional predicate is also 0, and Q is the target predicate. That superscript is just an index, meaning that this is the first template. In this paper, they limit it to only 2 templates. Okay, only 2 templates, and they do that because the number of templates appears in an exponent in the complexity result that I'll show you later. So it gets really nasty really quick. And we'll get into complexity a little later. Let's continue with the example. All right, so I'll show there's 8 clauses that can be generated with this template, and here they are. Now you got to generate all of them, but when you do, you can prune away some of the ones that are redundant. So that's what happens here. These go away or you can prune elements of the body that are redundant, but you also actually get redundant rules as you enumerate them. All right, so let's look at another example template, number 2 for this. And here, we'll change this up a little bit. 1 existentially quantified variable in the body and 1 intentional predicate in the body. So here's how that looks. And there's 58, and we'll show the 16. And by the way, in case you didn't see the subscript, this is all in Appendix B of paper. But here's just a listing of them. And again, well, some of them could be pruned away. I think they weren't redundant ones weren't shown. All right, so let's associate these with some Boolean flags. So here's a set of Boolean flags. So that I index is for your template number. The J index is for the clause within that template. And the P is your intentional predicate. In this case, we just got the 1. So this statement here, all this is saying Fijp is true if and only if the clause is in the rules in your solution. And we already talked about the, well, actually, in addition to the number of templates, the authors are only picking 2 clauses. And again, this is another exponent in the complexity result. Because they're searching a combinatorial space of combinations of rules. And there were some technical reasons as to why they went this way, as opposed to picking a subset like that. So here's your generated clauses with this guy tacked on. Other thing to note, the authors only allow 2 atoms in the body of each rule. Only 1 or 2 atoms in the body of each rule. Again, this is due to complexity. And here it is for the second template. No big surprise there. You just got those F's conjunction on the end. All right, so picking a set of Boolean variables. In this example, we're not going to say how it's done. That'll come a little later in the talk. But really, all this mathematics is saying is, hey, we're looking for a set B union F such that, for everything, for all the F's that are picked, the clauses union with them entail the target atom. And for everything that's outside of the positive set, they're not entailed. So of course, the set of rules, again, is just clauses such that the set F, this is just a set of these Boolean flags that are positive. And identifying the solution, in this case, if you make these 2 flags true, that actually gives you a solution. And so here are the associated clauses, and here's what those rules actually are. And this is a solution to this example. Right? So it's always funny in mathematics how I can give a super technical talk of just how it's set up, what the solution is, and I haven't told you anything about how it really works. That's always fun, right? Yeah.
I have a question. So I thought the first rule was proven in the previous process.
No, because it was only proved if there was a duplicate.
But PXY and PXY on those.
Oh, yeah, so actually, you're right, you don't need the second PXY because it's conjuncted with itself.
Okay.
So, but it's not pruned, it's just a redundant element.